Rightio superstars, we're going to continue with enzymes. You're learning intention. Enzymes have specific functions and are affected by factors including temperature, pH, and the presence of inhibitors. Really important ideas, all of these. You're going to need them in your deconstruction and design. Right, so just a quick note for you to take down those things. Three main factors that affect enzyme activity. Temperature, pH, so that's how acid or basic something is, and the presence of inhibitors. Inhibitors, things that stop enzyme action, and we're going to look at that in detail. Right, so bit of a busy slide, but it's all there for a reason. So firstly, let's think about chemical reactions and what's happening when chemicals are reacting. Look at this GIF over here. Particles colliding, right? There's lots of energy, particles are colliding, those collisions are causing products to be formed. So at low temperatures, over here, low temperatures, there's less energy in those reactants, less productive collisions, and less products being formed. The same thing happens with enzymes. Think about these blue dots being enzyme, and then the red dots being substrate. The faster they're going, the faster they're colliding, the more products are being formed. Okay, but now if we think about as we're increasing temperature, more collisions, more productive collisions happening, but that also puts stress on bonds. And we know that enzymes have lots of secondary bonds, and secondary bonds are not strong, they're weak. So we will get an increase in product formation, but once we get to a temperature that puts so much stress on the bonds that they begin to break within the enzyme, the active site changes shape, the enzyme changes shape, it unravels and it can't do its job anymore. When an enzyme unravels because its bonds are being broken, we call it denaturation. So down here we can see the tertiary structure of an enzyme, and then when there's too much energy in the system, the secondary bonds break and we end up with a denatured protein, which is just that squiggly polypeptide that we can see there. So the way that that looks on a graph, if you look over here, we have the rate of the reaction. So for this black enzyme, as the temperature increases, we get more and more productive collisions happening per unit of time. And that increases until this point here, at 37 degrees Celsius. So that's going to be our enzymes. Our body temperature, 37 degrees. That's good for us. That's good for our enzymes. But once our temperature goes past that, our enzymes start to denature and they cannot do their job. They can't break down the substrate, and so we don't get products being formed and the rate of reaction drops dramatically. So there are some enzymes that have this lower optimum temperature and some enzymes have higher optimum temperatures. So different enzymes will have different optimum temperatures. Right, so pH, similar but different. Okay, so pH, enzymes also have an optimum pH. Remember, low pH means acid, and higher pH means basic. In the middle, pH 7, that's neutral. pH 7. Alright, so what we find with pH, what we actually have are charged particles. You may or may not know that acids put H plus hydrogen ions into the solution. So if there's hydrogen ions in the solution, that means they can interact and interfere with the secondary bonds that hold the enzyme into its specific shape. So if we interfere with those bonds, we can get some denaturation happening in the enzyme as well. And so what that means is, as we increase our pH, then the rate of the reaction is going to increase as well, up to an optimum, and then once we go past that optimum, the rate of the reaction decreases again. So here we've got lots of H plus, and here we've got more OH minus is the other one, and that's got a negative charge. Right, and again, different enzymes can have different optimum pHs. This enzyme has a low optimum pH because it resides in the stomach and needs, pepsin helps us to break down proteins, so it needs to be able to withstand the low pH environment of the stomach. But for trypsin, which is an intestinal enzyme, it's going to be closer to that neutral, and it's a slightly basic optimum pH for trypsin. So a change in pH can alter the charge on the amino acids in the protein, affecting the affinity or force of attraction of the active site for the substrate. All of that comes down to the shape of the protein, the shape of the enzyme. If we change the shape of the enzyme, it cannot do its job, and that is the key. I haven't put the pencil here, but you should take notes on this one. Rightio, enzyme inhibitors. So inhibitors do just that. They inhibit the reaction from happening. So there's two types of inhibitors, competitive and non-competitive, and it is what it sounds like. Competitive inhibitors will compete for space on the active site. So without a competitive inhibitor, we're fine. Substrate can bind, no problem, normal binding, products being formed. But if there's a competitive inhibitor in the way, then that's just going to block that substrate from getting into the active site and no products being formed. But a non-competitive inhibitor, and this is a really interesting one, it can bind to a site on the enzyme that's different to the active site. And what that does is it causes the shape of the enzyme to change. And then substrate cannot bind to the active site because it's no longer complementary to the active site. And we don't get binding, we don't get products being formed. And here are your notes for inhibitors. Competitive inhibitors have a complementary shape to the active site on the enzyme, or similar, or it's a similar shape to the substrate because we know that the substrate's shape is complementary. They bind to the active site and they prevent the substrate from binding. Non-competitive inhibitors bind to a different part on the enzyme, causing a change in shape of the active site, and hence the substrate won't be able to bind because its shape is no longer complementary to the active site's